When you're deep in the weeds building these massive AI models, these LLMs, you sometimes feel like you're just hitting the same walls over and over. You start out, right? You train vanilla transformers.
Yeah.
Full of optimism.
Yeah.
And then, bam, they choke on long context, quadratic pain. It's like, yeah, that feeling when the compute cost just explodes. Okay, so pivot time. You try linear attention. It's meant to be efficient, faster, right? But then, it compresses too hard, loses retrieval, fumbles reasoning. You end up with this thing that's fast but kind of dumb sometimes. It can be super frustrating.
Yeah, it really can. But then sometimes you have this moment. You realize state updates aren't just additions, they're classification. That shift in perspective, seeing it not just as adding data, but organizing it, categorizing it as it comes in, that's the core insight here.
And that specific aha moment is exactly why we're doing this deep dive today.
Yeah.
We're looking at a really interesting paper just out July 22, 2025. It's called Scaling Linear Attention with Sparse State Expansion, or SSE for short.
Right. And our mission really is to unpack these two big ideas they've got. First, this whole new way of thinking about updating the model's memory classification thing. And second, a super clever way to actually expand that memory without making the model huge and slow. The goal is bridging that gap, getting the efficiency and the smarts, especially for really, really long texts.
And just to give everyone a taste of why this is exciting, they have this result, right?
Oh, yeah. Get this. Their 2 billion parameter SSE hybrid model. It achieved state-of-the-art mathematical reasoning performance among small reasoning models. I mean, for a model that size using this kind of efficient architecture, that's pretty surprising. It kind of challenges what we thought these models could do.
Okay, so clearly something cool is happening here, but let's back up a bit. Why is this such a problem? Why do even the standard, powerful transformer models struggle so much when you feed them, like a whole book?
Well, the big one for transformers is that quadratic computational complexity. What that really means is if you double the length of the text you're feeding it, the amount of computation needed doesn't just double, it quadruples.
Oof. Yeah, that scales badly.
Terribly. And then there's memory. During inference, when the model is actually generating text or answering questions, this thing called the key value cache, or KV cache, it just grows linearly with the input length. It eats up memory like crazy. So for massive documents, forget it. It's just not efficient.
Right, which is why people started looking at linear attention models. They're supposed to fix this efficiency bottleneck. What was the promise there?
Exactly. The promise was efficiency. And they do deliver on that front mostly. They get you sub-quadratic complexity, so the cost grows slower, which is good. And they have this RNN, like constant memory usage during decoding. So memory doesn't keep growing indefinitely.
Sounds great.
Yeah.
What's the catch?
The catch is how they achieve that efficiency. They basically compress all the information from the context into these really small, fixed-size state matrices. Think like 128 rows deep or something tiny like that.
Oh, so you're squeezing a potentially huge amount of info into a tiny space.
Precisely. And that aggressive compression, it often compromises performance on tasks such as in-context retrieval and reasoning.
Okay, and why specifically those tasks, retrieval and reasoning?
Because those tasks really depend on the details. Think about finding one specific fact in a long article or following a chain of logic. That relies on fine-grained token-level information flow. When you smush everything together into that tiny state matrix, you lose that precision. All the nuances get blurred.
Gotcha. So that sets up the big challenge the paper tackles.
Yeah.
How do you compress context efficiently without losing all that crucial detail? How do you get the best of both worlds?
Oh, exactly. How do you balance fidelity and efficiency? That's the key question.
Okay, so this brings us to their first big idea. They didn't just tweak the existing methods. They fundamentally rethought how the model's state, its memory, gets updated in linear attention, not just adding data, but classifying it.
Yeah, that's the core concept. They looked at the key vector, which is a standard part of attention mechanisms, and said, what if this isn't just input? What if it acts like a classification function? Basically, it decides where the incoming information should be filed away in the model's memory.
Okay, interesting. So if that's the new way, what was wrong with the old way, the sort of vanilla linear attention approach to updates?
Well, they identified two main issues. The first they call interclass mixing. See, traditional linear attention just kind of adds the new information to all the memory rows every single time step.
Oh, wow. Okay.
Yeah. So imagine information about say, physics getting mixed in with information about poetry in the same memory slots. It creates noise and interference from unrelated classes. It just blurs everything together, like trying to keep your notes organized by throwing every new note into every single folder you have. It's chaos.
Right. That sounds messy. And what was the second problem?
The second was forgetting. Because they applied this uniform decay factor to all the memory rows, basically making older stuff fade away to make room for newer stuff, it meant important information stored earlier just got washed out. Even if it was crucial, the recency bias meant it would eventually fade simply because newer stuff kept coming in and diluting everything.
Okay, so mixing and forgetting. That sounds like a recipe for a pretty unreliable memory. How did they fix it? What's the clever solution here?
So you design row-sparse updates, softmax, top K, hard selecting rows, cutting cross-class noise. They came up with this row-sparse update formulation. Instead of smearing the update across all rows, they use a softmax-based top K hard classification strategy.
Okay, break that down a bit. Top K hard classification.
Right. It means the model first classifies the incoming information, decides which category or class it belongs to, and then only updates the memory rows corresponding to the top K predicted classes. Usually K is very small, like 1 or 2.
Oh, so instead of writing everywhere, it picks just 1 or 2 specific folders to put the new info into, leaving the others untouched.
Exactly. It's like having highly specialized compartments in your memory. New information only goes into the most relevant slot, preserving the integrity of the information stored elsewhere.
That makes intuitive sense. What are the benefits of doing it that way?
Well, you get much higher inter-row discriminability. The memory slots stay distinct and more precise information organization. And crucially, because each memory element isn't constantly being overridden or decayed, it undergoes fewer decay operations. This effectively extends the receptive field over longer contexts.
Meaning it can remember things from further back?
Yes, which directly improves the model's retrieval performance. Suddenly, receptive fields stretch longer, state rows grow distinct, no more blurry overlap.
And they could actually see this happening. They had proof that the memory was getting more organized.
They did. They showed visualizations, figure 3C in the paper, demonstrating low row-wise similarity between the different memory rows when using this method. It was clear evidence the classification was working, keeping things separate, and they ran synthetic tests, these MQAR experiments, which also clearly showed the benefits of top updates for information recall.
Okay, that's really cool. Making the memory update process smarter, more targeted, but you still have that fundamental problem you mentioned earlier. Linear attention models usually have a really small, fixed-size state. Like the total number of folders is tiny compared to what a transformer implicitly uses. You hit a wall. Small state size strangles capacity. So even if the updates are smart, if the overall memory is too small, you're still limited, right?
Absolutely. That's the next big hurdle. And it leads to the crucial question. You ask, can we expand state without exploding params? How do you give the model more memory capacity without just making the whole thing gigantic and losing all the efficiency gains?
And this is where their second big innovation comes in. Sparse State Expansion.
Exactly, SSE. It was designed precisely to mitigate the memory capacity constraints caused by limited state sizes.
But how does it work? How do you expand the state sparsely?
Okay, so you invent Sparse State Expansion, SSE, split state into n partitions, share all params. What they do is expand the state into n partitions. You can think of it like having n separate smaller memory banks instead of one monolithic one.
In independent things.
Okay, but here's the really clever bit. All these partitions share attention parameters, the actual learned weights for calculating attention. They're the same across all n partitions.
Whoa, okay, why is that important?
Because it effectively decouples parameter size from state capacity. You can increase n, adding more memory banks, making the total state size much larger, but the number of parameters the model has to learn doesn't increase proportionally. It stays almost constant.
That is clever. So you get bigger memory without a huge model.
Yeah.
How does it decide which partition to use at any given time?
It uses a learnable bias for partition selection. Basically, the model learns to predict which of the n partitions are most relevant for the current input token. It picks the top k most relevant partitions. And then within those selected top k partitions, it uses the row-sparse update mechanism, we just talked about the softmax classification, to pick the specific rows to update. Learnable bias picks top k partitions, then softmax selects rows, state scales, parm stay lean.
Wow. Okay, so it's a two-stage selection process. First, pick the right memory banks, then pick the right folders within those banks. What does this do for the memory itself?
The results are pretty clear. SSE leads to lower inter-row similarity and higher singular value entropy. That basically means the different parts of the memory are storing more diverse, unique information, and the capacity is being used more effectively. They even show visually, in Figure 3, that the state matrix develops this diagonal pattern, which is strong evidence of effective information classification and separation across both rows and partitions.
So the big win is scaling up memory without the usual cost.
Exactly. It enables scaling up the state size of linear attention while keeping both computational and parameter overhead nearly constant. More memory, same speed, same model size, essentially.
That sounds almost too good to be true. How did they actually implement this efficiently? Making it work fast in practice must have been a challenge, especially with variable text lengths during training.
Yeah, implementation is key. They developed two main strategies. For shorter sequences, say up to maybe 1,000 tokens, which you often get in pre-training, they use a masking-based technique. It involves basically replicating the input data and then using masks so each partition only sees the tokens assigned to it. It works well for those shorter, varied lengths.
Okay, and for longer stuff?
For longer sequences, like in long context fine-tuning, they use a more optimized approach called the Varlin technique. This one is neat. It actually reorders the input tokens, grouping them by which partition they're assigned to.
So all the tokens for partition 1 are together, then all for partition 2, and so on.
Exactly. This lets them process all partitions in parallel very efficiently without wasting computation on masked-out tokens. And this is where they get that amazing scalability. You reveal the Varlin trick, scales with state size, runtime barely blips. The paper shows that this technique exhibits favorable scalability with respect to state size n, maintaining nearly constant runtime when k is fixed. Add more memory partitions, the speed hardly changes.
That's seriously impressive engineering. Okay, so the theory is smart, the implementation is fast. Let's talk results. Did SSE actually deliver in benchmarks? How did it stack up against other models?
The results are pretty strong across the board. If you look at just pure SSE without the hybrid elements yet, models like SSE-N4 showed strong results among advanced linear attention models, and they even managed to outperform transformers at the 600 million parameter scale on some tasks. You test pure SSE, crushes other linear models on retrieval, narrows transformer gap. And crucially, on real-world retrieval tasks, SSE consistently outperforms other linear attention models, really starting to close that gap with standard transformers.
Okay, better than other linear attention models closing the gap with transformers. What about the hybrid version, SSE-H? That mixes in some standard attention layers, right?
Right. And that's where things get really interesting. You build SSE hybrid, SSE-H, mix a few softmax layers, watch it soar. The hybrid SSE-H further boosts retrieval performance, actually surpassing other hybrids like GLA-H and getting closely approaching transformer-level accuracy on retrieval. Wow, okay. And when they scaled things up, pre-training on 2 trillion tokens, extending the context window to 32,000 tokens, SSE-H remained competitive with the transformer baseline across all task categories. But not just competitive, it actually achieved higher average accuracy overall, even beating the transformer baseline on tough benchmarks like MMLU, MMLU Pro, and CEVOL.
Beating the transformer on MMLU, that's significant.
It really is. And they even did this cool experiment where you convert pre-trained transformers to SSE-H. They took existing transformer models and swapped in the SSE-H architecture. The result, they retain power, gain efficiency, which is a huge potential pathway for upgrading existing models.
Okay. Retrieval looks great. General benchmarks look great. But the big one, the criticism you always hear, they say, but linear attention can't reason. Did SSE-H manage to crack that nut? Especially for something like mathematical reasoning.
This is probably the most headline-grabbing result, honestly. Our 2B SSE-H model after RO, 64.7 on AME24, 51.3 on AME25 smokes same-size transform.
Well, say those numbers again.
Yeah, a 2 billion parameter SSE-H model after reinforcement learning fine-tuning hit 64.7 on the AME 2024 benchmark and 51.3 on AIM 2025. That is state-of-the-art mathematical reasoning performance among small reasoning models.
Compared to similar-sized regular transformers.
It blows them out of the water. We're talking gains of like plus 16 points on AM24 and plus 14 points on AME25 compared to a model like Quen 3 1.7b. You show the math benchmarks. It outperforms, even beats bigger models. Its performance gets close to much larger models, like 7 billion parameter ones.
That completely upends the idea that these efficient architectures can't handle complex reasoning.
It It really does. It basically proves that hybrid linear attention can match softmax attention and mathematical reasoning ability, provided you train it right. That common wisdom might need rethinking.
Fascinating. And what about scaling the state size itself? You mentioned adding more partitions and n. Did that consistently improve things like recall?
Yes, very consistently. You scale state partitions, recall climbs, linear with n no parameter bloat. They found that recall performance improves approximately proportionally with n, the number of partitions, as long as the sparsity ratio, K7, stays constant. More memory partitions directly led to better recall, just as you'd hope.
Okay, so this sounds incredibly promising. But no research is perfect, right? What are the limitations they acknowledged? Where does SSE still fall short?
They're quite upfront about it. For instance, they tried incorporating more complex update rules, these delta rule mechanisms, but didn't see significant retrieval improvements there. So there might be limits to how complex the update needs to be. And while SSE-H is great, the pure linear SSE model without any hybrid softmax layers still has a notable retrieval gap compared to a really well-trained transformer. So for pure efficiency, there's still a bit of a trade-off on some tasks.
Makes sense.
They also mentioned that the way they currently select partitions, using only the current input context, this context-only hard selection mechanism, might not be the absolute best way. There could be smarter approaches.
So what are they planning next? Where does this research go from here?
Well, they want to dig deeper into this state scaling law for SSE. How exactly does performance scale as you add more partitions? They mentioned possibly using an uptraining scheme where you take an existing trained model and expand its state size, which is an interesting idea.
Yeah, adapting existing models.
Right. And they want to make the partition selection smarter, maybe by incorporating positional and historical information into the bias term, not just looking at the immediate context. And finally, exploring more sophisticated classification functions beyond the current softmax approach, maybe things that are state-aware, could push performance even further.
It really feels like, looking at all this, you didn't just tweak attention, you reimagined how models compress context.
Yeah.
It's more fundamental than just another attention variant.
I think that's a great way to put it. It's not about linear versus softmax anymore, or at least not just about that. It's about smart classification, sparse growth. It's about building memory differently.
Yeah, it's like they didn't just build a slightly better mousetrap. Your model balances speed, capacity, and smarts. They've created something that manages that tricky triangle really well. You know, people might say, but it's just 2B params. You point to it outperforming larger models on reasoning. They might say long contexts are niche, but you show it nails retrieval and scales beautifully. It feels like they built a bridge.
A bridge between efficiency and genuine long context understanding.
Yeah. So to wrap this up, let's leave our listeners with something to chew on. Thinking about this technology, the smart classification, the sparse state expansion, what happens when AI models can genuinely handle context of almost any length, maintaining both speed and that fine-grained precision we talked about? What new frontiers does that open up? Think about complex scientific research, pulling insights from vast data sets, or truly personalized education, adapting to everything a student has learned, or even understanding nuanced historical events from massive archives. What becomes possible when memory is no longer the bottleneck?